Right, well, thanks very much, everyone. It's been great to have some conversations with you guys. I've met quite a few of you over the last 1 or 2 days. The talks have been fantastic. The tour yesterday was fantastic. Looking forward to the tour this evening. So I'm Toby Potter, and I have a HPC consulting/education company right here in Perth. And I'd like to talk to you about some work I've done in a former life as a postdoc at the University of Western Australia. So just one vendor slide. So Pelagos, that's the company that I have. The name is Greek for the deep, or the deep sea. And the mission of Pelagos is to really help you get more from the depths of your data. And to do that, I'm providing training, currently in all things to do with Python, or as many things to do as I can put together. Some consulting in high-performance computing, and scientific software development and optimization services for industry and academia. So if you guys have any software that you need optimized, you have any training needs that you need done, I can help with that. And I have 9 years of experience in HPC to back that up. And so there's my website and LinkedIn profile. And so moving on to the talk. So this has UWA branding on it because it was research that was conducted as part of my former research group at UWA. And these are my former supervisors here, Jeffrey Schrag and David Lumley. So kicking things off, computational seismology plays a crucial role in exploration and reservoir monitoring. So you saw from Sean's talk yesterday that it costs $200 million to drill a well. A much better way to, not much better, but a better way to find out where resources are is to do some seismic experiments first. And so how they're done typically out in marine environments is you have this really large boat here, and that's towing this really large array. And there's an array of air guns here, and they're basically a seismic source. So let's bring the analogy to this room here. So let's pretend that you've put the microphone recorder, or you've turned on the microphone recorder for each of your laptops. And what I do is I make a noise, and then you guys record all that on your laptops. So you bring all that data, that information in, and what happens in the Earth is that these sound waves, they propagate into the Earth, and they reflect off discontinuities in the rock, so layers in the rock, anywhere where the velocity changes. And typically only 1% of that energy makes it back to the surface. Most of it goes down into the rock. But that 1% is very important, and that 1% can be used to do imaging, or to find out where those reflective layers are. And it turns out that oil and gas reservoirs are quite reflective. So that's why that seismology, or computational seismology, or reflection seismology in general, is used to find oil and gas reserves. So this is the power of 3D seismic. Now, reflection seismology is 100 years old now, and various techniques have been developed. And how they would do it with reflection seismology is that, so, you know the data that I just asked you to imagine that you recorded on your laptops? We'd collate that data, and in software you'd actually run that data backwards. So you'd push these received wave fields into the Earth. And depending on the seismic reflection method that you use, you can correlate this received data with a synthetic source data that you generate in a computer. Okay, so that correlation has happened, and the field of reflection seismology is maturing, or is mature, and it can produce these beautiful images of the subsurface. Okay, so a geologist can have a look at that, and they could tell you whether or not there's good potential for oil and gas reserves. So the physics of wave propagation has gotten more and more complex. The simplest wave propagation physics just involved an acoustic approximation. All we dealt with was acoustic waves, and all we dealt with was the first arrivals of those waves. But more and more complex, in order to get better results for your imaging, you need to resort to more and more complex descriptions of the physics. So in addition to acoustic waves, which are compressional, there is shear waves, which is kind of like this, or this. So these shear waves, and there are algorithms, so there are equations and algorithms that describe not just the compressional, but also the shear waves. And these are called elastic wave equation propagators. And if you go further, if you consider that energy is actually being lost in the shear waves as the waves are propagated, you actually need a higher description called visco-elastic wave propagation. And so as we move on, companies like Woodside will be looking, and Doug would be looking to use more and more complex descriptions of the waves. But in order to solve these waves, in order to propagate these waves in software to do your imaging, you need a lot of compute resources. Okay, so this is an image here of the subsurface of a synthetic model, and this is a wave, a simulated wave being propagated through the model. Okay, so that would be from a source, and that source wave would be correlated with your received data in order to find out where the differences in velocity are. So these things here. So what I'm saying is that we need lots and lots of compute in order to propagate these waves so we can get more and more accurate seismology results. So the tool to use to do computational reflection seismology, all their compute hardware. But one thing to note is that the CPUs that we use to do these computational kernels, they're not getting any faster in terms of clock speed. Moore's law is still continuing in terms of the number of transistors, but performance is actually gained now by increasing the number of cores in the machine and also increasing the amount of work that a core can do per clock cycle. So, due to power limitations, clock rates on CPUs are not getting faster. And as I said before, performance is now obtained by increasing the number of cores and increasing the work done per clock cycle. And so these are some processes of note. Can anyone tell me which machines they correspond to? Go ahead, Dave. Correct, that's right. And there's some things to note from this. The clock speed has actually decreased from Epic to Athena. The number of cores has greatly increased, and the amount of flops that they can do per clock cycle has increased. So how can we make use of these architectural gains? Well, to get more out of your more cores per socket, we can use OpenMP, OpenCL, OpenACC, MPI, CUDA, Silk. For more work per clock cycle, we resort to compiler vectorization, OpenMP, SIMD to do this explicitly, OpenACC and OpenCL. The thing is, though, that compilers, if you're just relying on compiler vectorization, compilers are very conservative about implementing SIMD vectorization. So that's the more work per clock cycle. And so my contention is that software that is not engineered to exploit both forms of parallelism will not benefit from future developments in processor architecture. So how this affects exploration? Well, time to solution is crucial for your business, crucial for anyone's business. Processing flows are being developed all the time. More and more advanced physics is being incorporated into these solvers. And often processing flows rely on research software that has been brought into production. Okay, so your research and technical department might come up with a new way of solving an algorithm, and you might decide to press that into production. And so research software is often written by scientists and engineers with less emphasis on scalability and leveraging modern computer architecture or features of modern computer architectures. So consequently, as hardware architectures evolve, production codes will increasingly lack the ability to benefit from the hardware advancements unless they're modernized. And I'm actually going to demonstrate that to you today with today's results. So there's my outline. Okay, so at UWA we have a challenge, and that's to simulate elastic wave fields in a very large representative 3D model of oil and gas fields off Exmouth. Okay, this is part of our research consortium project with UWA and our industry partners. The model is huge. It's 16K by 8K by 1200 by 5 components. And so that's 3 terabytes there of 32-bit floating point cells. So it's a really large model by the industry standard. And so our goal is to simulate 3D visco-elastic wave propagation through this model and generate synthetic data that our industry partners can use to test their imaging algorithms. And the code we use to do this is a community code called Sofi. It uses a staggered grid finite difference time domain modeling approach. It uses the velocity stress formulation for solving the isotropic viscoelastic wave equation. It's a simple domain decomposition, so you're not doing block structure, domain refinement, or anything else like that. It uses MPI, and it's written in C. So that's the tool that we started with. And so here's the equation that it's solving. There's only one equation in this talk, but this is the seismic wave equation here. And these are velocity components, that's density. This is the stress tensor, and that is the source term that you get from your explosive source. And so at second order time, accurate eighth order space. And this is how the algorithm works. You first update these velocity components. You do a velocity exchange with your MPI processes. You do a stress update and then followed by a stress exchange. So if this was 2 MPI processes, you do your velocity update, they do a velocity exchange with each other, so your domain will be decomposed into 2, followed by the stress update and then the stress exchange. So we got 4 million core hours on Magnus, so thank you very much to the Pawsey Time Allocation Committee. And I set to work in testing Sofi 3D for this application. So I used 12 nodes of Magnus with 16 MPI processors per node. I know there's 24 available, but I chose to use 16 because of cache thrashing. I didn't want to have any of that. I divided my domain into square cubes of 48, 64, 96, 128 on the side, and I ran it for 6,000 time steps. So I used the GCC and the Intel compilers just to try out 2 different compilers. I know the Cray compiler is there, but it didn't work with our software environment, so we discarded that idea. Okay, here's our initial profiling results. This here in the green is the stress exchange. This here is the stress update. In the yellow is the velocity exchange, and in red is the velocity update. On the y-axis is the computing expense. Now I've said core seconds per cell per time step is the computing expense. I think that's a good metric because it gives you a nice figure that you can generate first order approximations to the compute time. So if you have so many cells or so many time steps, you can get an estimate of how expensive that compute is going to be. So you can think of this as a proxy for wall time. Okay, you can see with the GCC compiled version, so this is with 838 cubes, so 8 in the x direction, 3 in the y direction, 8 in the z direction. Okay, you can see that In the first 3,000 iterations with the reference implementation, there's an awful lot of time being spent in the communication. With the Intel compiler, we didn't see that as much. Now, I'm not really sure why this is, but I've got a good hypothesis. If we load this up with Intel Trace Analyzer, so this is time on this axis, this is process ID, and red is when you're waiting. Okay? So this is with the GCC compiler, and this is with the Intel compiler. They're both using the Cray MPI libraries, so I don't think that's a problem. I think it's really compiler specific here. And so here's what I found that was going on. Now, can I get my volunteers to come up? I'm going to need one more. I need one more volunteer. Andreas, you want to have a go? Sure. Okay, can I get you guys to arrange yourselves into a grid? So I need one person here, one person behind you, one person next to you, one person behind. Yep, that's right. Okay, so there's a few simple rules, and so this is how Sofi worked in its reference implementation. All right, a few simple rules, guys. If you can, I want you to do a high five in this direction or this direction, but only after you've done a high five in that direction. Then I want you to do a high five in this direction. Okay? All right, so you can't do a high five in this direction, so you're a boundary condition MPI process. All right? So yep, so you come a bit closer, tighten up the grid a bit. So each of you are MPI processes. I'll tell you when to start. I'll tell you when. Each of you are MPI process, and you have a portion of the grid, right? Okay, so I'll do a high five in this direction, but only after you've done a high five in this direction, can you then do one behind. Okay, go. Yep, so you guys? Yep. Only after you've done it in this direction, then you can go in that direction. Okay, so that's the first iteration. It's a little bit slow, but we'll try again. Okay, we've got in this direction, go. Yep, behind you. That's it. Okay, everyone in the grid is going to do a high five in that direction first. Okay? Well, yes, I know. Right, so if you can, do a high five in this direction first. So everyone does a high five in this direction or this direction first, and then a high five in this direction second. Okay? Okay, go ahead, go. High five in that direction. Now it's cross direction. Look, that's it, cross direction. You come this way. Okay, fantastic. All right, so we've got one successful iteration there. And so that's what was going on with the reference implementation, right? It was doing its exchanges in this direction, and then it was doing its exchanges in this direction. But what it was doing is that, okay, now we're going to try another iteration, but Jean, you're going to take your time to do a high five, okay? So you're not going to do a high five at all until I say. Okay, we'll try it again. Okay, ready, set, go. All right, now do yours, Jean. Okay, now you can do this direction. All right, can you see how Jean has actually affected the whole cluster, the whole set of MPI processes. Now that's blocking communication for you, okay? And that's what was going on with the reference implementation. Let's give these guys a hand. Thanks very much. Okay, so that's what this red is here. These MPI processes are waiting for a slow MPI process to finish its work. All right, so let's fix this. Engineering a solution and making sure it's right. So what I found with Sofi is that the innermost loops of the velocity and stress updates were not making use of modern CPU features. They weren't vectorizing. Okay, regardless of which compiler was used. That was for both the GCC and Intel. There was inefficient blocking MPI communication between processes. Each MPI process had to wait for the other person in order to complete the transaction. The memory allocated in capture of seismic data. So what was going on was that every MPI process had the memory allocated for the whole space. So everyone in the room had everyone else's data. So that made it impossible for large-scale modeling. And it had some fairly slow pointer-to-pointer based memory access, so pointer jump. So from pointer to pointer to pointer memory access. And so I implemented a whole raft of fixes. So I fixed the MPI, fixed the slow serial I/O reads with templated MPI reads. I replaced some of the divisions with multiplications. I flattened the array access. So to use, instead of pointer to pointer to pointer, just using simple one-dimensional array access. I changed the memory alignment. Now when you do a standard malloc, I believe it aligns memory to 16-bit boundaries, but vectorization, or more advanced vectorizations like AVX, require at least 32, okay? So I had to actually explicitly fix the memory allocator so it would allocate memory in multiples of 32 bits. Fixed up the MPI communication. So instead of using synchronous MPI communication with MPI send, receive, replace, I use combinations of MPI I send and I receive. Okay, so that means that it's more of a letterbox analogy now. Instead of doing high fives, each of these people could leave information in the other person's letterbox. And then when that person's ready, they can grab that information. And I fixed some of the output as well. And so we had some talks. We had a talk today, also had a talk yesterday about comparative debugging. Well, here are some comparative, some comparisons between the reference implementation and the optimized implementation. So this is just a shot gather. So this is just the wave information as a function of time and space. I just did a subtraction of the two, and that's what's important for seismic wave propagation. And the difference is 6 orders of magnitude less than the wave field here. So Jeff and David thought that was acceptable. 6 orders of magnitudes smaller difference than your data. So that was okay. And the difference was actually caused by replacing the divisions with multiplications. Okay, so this is the profile after the overhaul. I forgot to mention that this black line here was actually the requirements set by our compute time allocation. We had so many seismic experiments or shots that we wanted to do, and in order to get within that in order to do those number of shots within that compute time allocation, our code, the envelope of this, had to get faster than the black line. Okay, so these are the reference implementations here, and here's the optimized implementation. You can see that the amount of problems with the stress exchange are reduced in the GCC version, but with the Intel version, you can see the difference is quite dramatic. And what was actually happening here is that the Intel, with those fixes that I applied to the code, the Intel compiler was vectorizing, whereas the GCC compiler wasn't vectorizing still. It just gave up. And so with the vectorization turned on, I got a performance increase by about a factor of 2. So if we zoom in, we zoom into iterations roughly 3,500 to 6,000. You can see that with the optimized version, these spikes here have decreased a lot, and the overall execution time has been halved. And so this optimized version with the Intel compiler meets our target compute requirements. If we have a look at the speed up, so this is the Intel version which I've set to 1, and relative to the reference implementation, you can see with the Intel optimized version we're getting some increases in performance with the stress exchange, the stress update, and the velocity update. I forgot to mention that I had hidden some of the stress exchange behind the computation. So I computed a little bit of the stress update, then sent off the information to other MPI processes, and then I computed the rest of the interior for the stress update. And so the total speed up is around a factor of 2. And so with the GCC optimized version, the stress exchange benefits enormously from the step, and the numerics of the stress update and the velocity update also benefit. The velocity exchange is an interesting case. It actually appears to be worse under the optimizations, but I wasn't able, due to a bug, I wasn't able to hide the computation of the velocity update. So I wasn't able to hide the communication of the velocity update behind the computation. So this was blocking communication. And this is what it looks like without blocking communication. So this is with a non-blocking communication in place. And this region here is the stress update, and this region here is the velocity update. And you can see that the amount of wasted time has been greatly reduced with the introduction of non-blocking communication. Okay, so if we apply this to our large-scale modelling problem, this is just a velocity model and a density model. And this is some of the results that we got out of it. So using that code, we successfully generated all 2,700 shots that we needed for the project. Okay, so conclusions from that. I successfully made an isotropic visco-elastic solver ready for production in a way that met our compute requirements. Non-blocking communication is effective at reducing unnecessary wastage of CPU time, and enabling vectorization within the code went a long way to giving us an approximately 2 times overall speed up. And investment in the Intel Parallel Studio Suite was crucial in achieving performance gains. And so what we did after that is we thought, well, what happens if we run out of our compute allocation? We might need to get supplement capacity from the cloud. So we deployed Sofi 3D to the Amazon cloud, and this is just geophysics in the cloud. So we called our Amazon cluster Tepuy, because it reminded me of these tepuis in Venezuela, so geophysics in the cloud. And this is the node configuration of Tepuy. So on Magnus, we have 24 cores, 64 gigs of memory per node. On Tepuy, we also have a similar configuration, 16 cores, 64 gigs per node. So I'm using the M4.4 extra large nodes. And this is our results. This is computing expense as before. And so lower is better. The blue ones here are the Magnus results for different subdomain cells. So different sizes per cube. So different side sizes per cube. And so, yeah, so the cloud compute performance was about twice as slow as Magnus. And I suspect that that's because of hyperthreading. So if you have a look at the architectural differences between the typical nodes and the Magnus nodes, it's not a factor of 2. But I think because AWS uses hyperthreading, we're getting this. And can you see this curve here, this bow curve? That's suggesting that there's a sweet spot in the cells per side. Does anyone know why that sweet spot would be there? Anyone make a guess? If we go as small as possible, our grids are going to fit within cache, aren't they? But on this side, if you go as large as possible, your communication overheads are going to be smaller relative to your compute. So you've got cache optimizations pulling you in that direction, and MPI optimizations pulling you in that direction. And so that's why then you'll get a sweet spot of how many subdomain cells per side that you have. So my final conclusions, we tried Sofi 3D successfully on Amazon. Vectorization did work within virtual machines, and the optimization, it's around twice as expensive as Magnus. So how much, if you were a company and you had to do this project purely on AWS resources, using spot pricing, so that's 22 cents per hour per node, this optimization would have saved you $100,000. And so it's really important to be able to have a look at your codes, optimize them, and get them running as efficiently as possible. And I just want to thank our UWA Research Consortium, of which Doug is a member, our WEMO industry partners, and the Pawsey staff and time allocation committee. Thank you. Right, yes. Right, yep. Yep. Yes, yep. Yeah, that's true. I mean, jumping to the cloud is a way to avoid delays in queue time.